In the previous tutorial, we familiarised ourselves with the structures of decimal, binary, and hexadecimal numbers, and how to lay them out in columns according to their respective base powers. Decimal uses base 10 structure, so each digit represents a rising power of 10 as we move from right to left. If we take an example decimal number of 315, there are 3 hundreds, 1 10, and 5 units, or 3 times 10 to the 2, plus 1 times 10 to the 1, plus 5 times 10 to the 0, or 3 times 100, 1 times 10, and 5 times 1, which gives an answer of 315. The same method can be used to convert binary and hexadecimal to decimal. We simply substitute the required base sets. Let's say I have a 16-bit word with an unsigned value. I can label the digits with their respective powers of 2 as I demonstrated in the previous tutorial. Then I simply sum the products as I did with the decimal system. Starting at the most significant bit, it is clear, and so that's 0 lots of 2 to the power 15, plus 1 lot of 2 to the power 14, plus 1 lot of 2 to the power 13, plus 0 lots of 2 to the power 12, plus 0 lots of 2 to the power 11, plus 1 lot of 2 to the power 10, plus 0 lots of 2 to the power 9, plus 1 lot of 2 to the power 8, plus 1 lot of 2 to the power 7, plus 0 lots of 2 to the power 6, plus 0 lots of 2 to the power 5, plus 1 lot of 2 to the power 4, plus 0 lots of 2 to the power 3, plus 1 lot of 2 to the power 2, plus 1 lot of 2 to the power 1, plus 0 lots of 2 to the power 0. This gives us 0 plus 16,384 plus 8,192 plus 0 plus 0 plus 1,024 plus 0 plus 256 plus 128 plus 0 plus 0 plus 16 plus 0 plus 4 plus 2 plus 0, which gives a final answer of 26,006. Now let's try an 11-bit unsigned word. We have 1 lot of 2 to the power 10, 0 lots of 2 to the power 9, 1 lot of 2 to the power 8, 1 lot of 2 to the power 7, 0 lots of 2 to the power 6, 0 lots of 2 to the power 5, 1 lot of 2 to the power 4, 0 lots of 2 to the power 3, 1 lot of 2 to the power 2, 1 lot of 2 to the power 1, and 0 lots of 2 to the power 0, which is the same as writing 1024 plus 0 plus 256 plus 128 plus 0 plus 0 plus 16 plus 0 plus 4 plus 2 plus 0, which gives a final answer of 1430. Now let's treat these same bits as a signed word. The most significant bit now controls the sign. It is set here, and so the result will be negative. The decimal value is determined by the same means as before, but it's not simply a case of working out the value and then making it negative. The most significant bit alone controls the sign, and so only the value contributed by that bit will be negative, and the rest will be done as normal. We start with minus 1024 because the sign bit is set, plus 0, plus 256, plus 128, plus 0, plus 0, plus 16, plus 0, plus 4, plus 2, plus 0, which gives a final answer of minus 618. Hexadecimal numbers use a base 16 structure, and so can be converted into decimal by the same method but using a base set of 16. Let's take an example hexadecimal word of 5AF6. First, we notice that it's a jumble of numbers and letters. As we saw in the previous tutorial, the letters A through F represent the decimal values of 10 to 15 respectively. With that in mind, I can enter the digits into their respective columns and apply the corresponding base 16 values. So we have 5 times 16 to the power 3, plus A times 16 to the power 2, plus F times 16 to the power 1, plus 6 times 16 to the power 0, which is the same as saying 5 times 16 to the power 3, plus 10 times 16 to the power 2, plus 15 times 16 to the power 1, plus 6 times 16 to the power 0. which gives a final answer of 23,286. Now let's look at converting decimal numbers back into binary. We've seen that binary is made up of combinations of powers of 2. Each set bit contributes its corresponding power of 2, while clear bits contribute nothing. I can use this principle to determine the binary representation of a decimal number. Let's take the decimal value 45,281 as an example. I need to first determine the minimum length of a binary word required to hold this value. A single bit has 2 states, 0 and 1. 2 bits have 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. 3 bits have 8 states, 4 bits have 16 states, and so on. This means the amount of states that a word of a given length can hold is simply given by 2 to the power of that length. Mathematically, I can write this as n bits can hold 2 to the n states. The number of states a word can hold must be larger than the number I want to store in them, otherwise it won't fit. I can determine the required word length by simply increasing n until the number of states becomes greater than my number. A 15-bit word will hold 2 to the power 15 states, which is 32,768 states. That's less than 45,281, and so will not fit. A 16-bit word will hold 2 to the power 16 states. That's 65,536 states, which is greater than 45,281, and so this will fit. We can now proceed to convert the decimal value to binary. As I stated earlier, the bits in a binary word will contribute their corresponding power of 2 to the overall value, while clear bits will contribute nothing. I will divide the value by descending powers of 2 starting from the most significant bit. If the result is greater than 1, then the bit is a 1, otherwise it's a 0. I divide 45,281 by 2 to the power 15, or 32,768, and the result is 1.381. This is greater than 1, and so the bit is 1. This bit therefore contributes a value of 32,768 to the overall number. Now that we've determined this, we need to subtract this out so that we only continue to work on the number which is made up from the remaining bits. I subtract 32,768 from 45,281, which gives a new number of 12,513, and we can now move on to the next column. I divide the new number of 12,513 by the next power of 2, which is 2 to the power 14, or 16,384, giving a result of 0.763, which is less than 1. Therefore, this bit is 0 and contributes nothing to the overall value, and so there is no subtraction. We simply move on. Next, 2 to the power 13, which is 8,192. The value is still 12,513, so I divide by 8,192, which gives a result of 1.527, which is greater than 1, and so the bit is 1. This bit is therefore contributing 8,192 to the overall value, so I subtract it out to give a new value of 4,321, and we move on. I continue to divide the overall number by the respective powers of 2 and set the bits accordingly, subtracting the power of 2 if it produces a set bit. I repeat the process on the new value until I reach the end. This produces a final bit combination of 1011 0000 1110 0001, which is the binary representation for 45,281. And finally, I've saved conversion between binary and hexadecimal for last, as it's really easy. I'll draw the binary truth table up to the value of 16 with the decimal and hexadecimal values included as a reference. I'll take my bit sequence from before as an example. To convert this binary string to hexadecimal, I simply split it up into blocks of 4 bits, starting with the least significant bit. I then look at the arrangement of each 4-bit block and match it to its corresponding hexadecimal digit in the truth table. Starting at the least significant bit, the first block is 0001, which is 1. The second block is 1110, which is E. The third block is 0000, which is 0. And the last block is 1011, which is B. So the hexadecimal value is B0E1. I can try another. Split into blocks of 4 bits. The first block is 1110, which is E. The second block is 0011, which is 3. The third block is 1101, which is D. And the last block is 0110, which is 6. So the hexadecimal value is 6D3E. This is easily reversible. If I was presented with the hexadecimal value of 58DF, for example, I know each digit represents a block of 4 bits, and so I can just use the truth table in reverse. 5 gives me 0101, 8 is 1000, D is 1101, and F is 1111. So the binary value is 0101, 1000, 1101, 1111. It also becomes clear why writing in hexadecimal is preferable over writing in binary, as it shrinks the amount of digits by a factor of 4. If I was to have a 32-bit binary sequence, such as this, you can see that there is a lot of bits. If I split these into blocks of 4, it converts to a hexadecimal value of ADF6, B6, B8, which represents the same value but only using a quarter of the digits, and is easily convertible back into binary if necessary. If you know how to count up to 16 in binary, then you can convert between binary and hexadecimal without the aid of a truth table.